Linear Algebra II, Lecture 13, Eigenvectors and Eigenvalues. Let us start with some motivation. Let V be a vector space and F be a linear operator on V. If we choose some basis in V, then we have the corresponding matrix of our linear operator F with respect to this basis. The matrix depends on the choice of the basis. So we can try to change the matrix by choosing a different basis. And then a natural question to ask is, how can we choose a basis such that the matrix of our linear operator in this basis is easy, or as easy as possible? Of course, it depends on what an easy matrix is. So one has first to decide what does one mean by an easy matrix. One possibility is that a matrix is easy if it contains many zeros. So the more zeros you have in a matrix, the easier it is. It's one possibility. But we will discuss this a little bit later during the lecture. So the idea of this part of the course is to define what an easy matrix is, to determine when you can choose a basis V such that the matrix of F in this basis is easy, and give an algorithm how to find such a basis and the corresponding easy form for the matrix of F. Let us do one example. Consider the identity map from V to V. We know that in any basis bold V in V, the matrix of the identity operator in this basis bold V is the identity matrix. So this does not depend on the choice of V. In particular, the identity matrix is as easy as one can get. One cannot make the identity matrix easier by choosing a different basis. So what are the properties of the identity matrix which one can observe? And one such property is that this matrix is diagonal. So how can one characterize diagonal matrices compared to how the linear operator, which is described by a diagonal matrix, acts on a vector space? So this is the first thing which we will discuss. So let's start now with the main definitions. Let V be a vector space and F a linear operator on V. Definition: a vector V in V is called an eigenvector of F with eigenvalue lambda, which is a real number, provided that F of V is equal to lambda times V. Another definition: a real number lambda is called an eigenvalue of F, provided that there is a non-zero eigenvector for the operator V in V with eigenvalue lambda. So here are some examples. Example 1. For any linear operator F, F of the zero vector is equal to the zero vector, and this is equal to lambda times the zero vector for any real number lambda. Therefore, the zero vector is an eigenvector for any linear operator and with any real eigenvalue. Second example, if we look at the identity linear operator, then we know that the identity linear operator applied to any vector V in V is equal to this original vector V. Therefore, any vector in V is an eigenvector for the identity linear operator with eigenvalue 1. Let us now talk about diagonalizable maps. Definition: a linear map F is called diagonalizable provided that there is a basis bold V in V such that the matrix of F in this basis is diagonal. Example 1, the identity map is diagonalizable, because if we choose any basis bold V in V, the matrix of the identity map in this basis is the identity matrix, and this one is diagonal. The second example, the zero map is also diagonalizable, because the matrix of the zero map in any basis is the zero matrix, and the zero matrix is diagonal. So our first observation about diagonalizable linear maps is the following. Theorem. A linear operator f on a vector space V is diagonalizable if and only if the vector space V has a basis which consists of eigenvectors for our linear map f. And the terminology, a basis consisting of eigenvectors for f, is usually called an eigenbasis. Let us prove this theorem. Let bold V be an eigenbasis for the linear operator f on V. So assume that this bold V eigenbasis consists of the vectors v1, v2, and so on, vk. Then, by definition, f applied to vi is equal to lambda I times vi for some lambda I, a real number. Therefore, if we write the matrix of f in the basis V, we will get the following matrix. The first column in the matrix consists of the coordinates of f of v1 in our basis bold V. So f of v1 is equal to lambda 1 times v1. So we will have lambda 1 in the first position and all remaining coordinates are 0. The second column consists of the coordinates of f of v2. So f of v2 is lambda 2 times v2. Therefore, we will have lambda 2 in the second position and all other coordinates is 0. And so on. The matrix which we obtain in this way will have lambda 1, lambda 2, and so on lambda k on the diagonal, and all remaining elements in this matrix will be 0. So we will get a diagonal matrix. Conversely, assume that V is a basis of our vector space V such that the matrix of f in this basis is diagonal, and namely the matrix which we have here, with elements lambda 1, lambda 2, and so on lambda k on the diagonal. Then, by the same argument as a minute ago, f applied to vi is equal to lambda I times vi. Therefore, each element vi in our basis bold V is an eigenvector for f, and hence this bold V is an eigenbasis for f in V. And this completes the proof of the theorem. Let us now discuss eigenvectors. Notation: for a real number lambda, let us denote by V of f comma lambda the set of all eigenvectors V in V for our linear operator f with eigenvalue lambda. Let us observe that this set, the set of all eigenvectors for f with eigenvalue lambda, coincides with the kernel of the linear map f minus lambda times the identity of V. Proof: we just rewrite the condition f of v is equal to lambda v. This is a condition which defines an eigenvector. We move lambda v to the left and write lambda v as lambda times the identity of v applied to v, and then f of v minus lambda v can be written as f minus lambda times of identity of v applied to v. And the condition that f of v is equal to lambda v is then the condition f minus lambda identity applied to v is equal to 0. So the eigenvector for v with eigenvalue lambda is the same thing as the element in the kernel of the linear operator f minus lambda times the identity of v. Corollary: v of f comma lambda is a subspace of v. So this follows directly since we know that the kernel of any linear map is actually a subspace. So since the set of eigenvectors is already described as a kernel of a linear map, it must be a subspace. Another corollary: a real number lambda is an eigenvalue of f if and only if the kernel of the linear map f minus lambda times the identity on V is non-zero. Again, this follows directly from our observation. This implies yet another corollary. Let bold V be a basis of our vector space V. Then a real number lambda is an eigenvalue of f if and only if the determinant of the matrix of the linear operator f minus lambda identity V in our basis bold V is 0. So this follows from our description of eigenvectors as elements in the kernel. So we know that the kernel of a linear operator is non-zero if and only if the homogeneous system of linear equations whose matrix is the matrix of our linear operator in some basis, so in particular in our chosen basis V, the system should have a non-zero solution. And since the matrix of our linear operator is a square matrix, because it's a linear operator on a vector space, a homogeneous system of linear equations with a certain square matrix has a non-zero solution if and only if the determinant of this matrix is 0. And this implies our corollary. And this naturally leads us to the notion of the characteristic polynomial. So let us first recall the notion of a characteristic polynomial of a matrix. Let M be a square matrix of size n times n. Denote by En the identity matrix of the same size. Definition: the characteristic polynomial of M is defined as the following polynomial. It is denoted by chi sub m of x, and it is defined as the determinant of the matrix M minus x times En. Observe that, by definition, chi sub m of x is a polynomial of degree n, and with the leading coefficient minus 1 to the power n. N is the size of the matrix. So for example, if M is the 1-by-1 matrix consisting of A, then the characteristic polynomial by definition is A minus x. The second example, if M is the general 2 times 2 matrix with entries A, B, C, and D, then the characteristic polynomial of this matrix is x squared minus a plus d times x plus ab minus cd. So a plus d is a trace of this matrix, and ab minus cd is the determinant of this matrix. Example 3. If M is a diagonal matrix with lambda 1 and so on lambda n on the diagonal, then the characteristic polynomial of this matrix is the product of the linear factors lambda I minus x. So now we can define the characteristic polynomial of a linear operator. So let f be a linear operator on a vector space V. Observation: let V and W be two bases in V. Then the characteristic polynomial for the matrix of f in V is equal to the characteristic polynomial for the matrix of f in W. Proof: let T be the transformation matrix from V to W. Recall the base change formula. The matrix of f in W is equal to T inverse times the matrix of f in V times T. Therefore, we can write the following, that the characteristic polynomial for the matrix of f in W is by definition equal to the determinant of the matrix of f in W minus x times the identity matrix. Now we use the base change formula to write the matrix of f in W as T inverse matrix of f in Vt minus x times, and we write the identity matrix as T inverse T. So we can move T inverse to the left and T to the right, and we write it as a determinant of T inverse times the matrix of f in V minus xen, and then times T. The determinant of the product is a product of the determinants. The determinant of the T inverse is equal to the inverse of the determinant of T. So these two things cancel each other, and what is left is the determinant of the matrix of f in V minus x times En. And this is by definition the characteristic polynomial of the matrix of f in V. And this proves our observation. Using this observation, we can define the characteristic polynomial of the linear operator f as the characteristic polynomial for the matrix of this linear operator in some basis V. And because of this observation, this does not depend on the choice of our basis V. So the characteristic polynomial for the linear operator is well defined. Now we can discuss eigenvalues. Let F be a linear operator on a vector space V. The consequence of the previous discussion is that the eigenvalues of F are exactly the roots of the characteristic polynomial for our linear operator F. In particular, it follows that the number of different eigenvalues of F is at most the dimension of V. So this follows directly from the observation that the characteristic polynomial is a polynomial of the degree dimension of V, and thus it can have at most dimension of V different roots. So let lambda be an eigenvalue of F. So we define the algebraic multiplicity of this eigenvalue as the multiplicity of lambda as a root of the characteristic polynomial. So if lambda is not an eigenvalue, then the algebraic multiplicity of lambda is 0, or we can define it also as 0. And another definition, the geometric multiplicity of lambda is defined as the maximal number of linearly independent eigenvectors for F with eigenvalue lambda. Alternatively, so this number is equal to the dimension of the kernel of the linear map F minus lambda times the identity map. And the main observation about the multiplicities is the following theorem, that for any lambda, the geometric multiplicity of lambda is at most the algebraic multiplicity of lambda. So here is a proof of the theorem. Let us denote by k the geometric multiplicity of lambda. Then by definition, we have k linearly independent eigenvectors of F with eigenvalue lambda. Let us extend this set of linearly independent eigenvectors to a basis bold V in V. Then, in this basis, the matrix of F has the following form. So the first k vectors are eigenvectors with eigenvalue lambda. So for the first k columns, we have lambda on the diagonal, and the remaining elements in these columns are 0. And then we have no information about the rest, so the rest can be arbitrary. But we now see that this matrix is block diagonal, so we have here lambda times the identity matrix in the beginning, and then some block here at the end. So the characteristic polynomial for this matrix is the determinant of this matrix minus x times the identity. So we will have lambda minus x to the power k from this block, and then some polynomial g of x from this block. But in particular, we see that the characteristic polynomial of f is divisible by lambda minus x to the power k. So the geometric multiplicity of lambda, which is k, is not greater than the algebraic multiplicity of lambda, which can be bigger if g of x is divisible by lambda minus x. So now we can formulate the algorithm how to look for eigenvalues and eigenvectors for a linear operator. So let F be a linear operator. So we start by choosing some basis in V and computing the matrix of this linear operator with respect to this basis V. Next, we need to compute the characteristic polynomial of this matrix, which is also then the characteristic polynomial for the linear operator. Next, we need to find all roots of these polynomials, and these roots are exactly the eigenvalues for F. And next, for each root lambda of the characteristic polynomial, we need to solve the homogeneous system of linear equations whose matrix is the matrix of F minus lambda times the identity matrix. And the basic set of solutions to this system, it gives exactly the coordinates in our basis V for a basis in the subspace of all eigenvectors for F with eigenvalue lambda. And in this way, we thus determine all eigenvectors with eigenvalue lambda. So here is an example. Problem: find all eigenvectors and eigenvalues for the linear map F from R3 to R3, which has the following matrix in the standard basis. So the matrix of F in the standard basis is 2, 1, 2, 1, 2, 2, 0, 0, 3. Solution. The first step here to do is to find the characteristic polynomial for our linear map. So it's the determinant of the matrix of f minus x on the diagonal. So we see that this matrix 2 minus x 1 2 1 2 minus x 2 0 0 3 minus x, it's a block diagonal matrix. We have 2 times 2 block 2 minus x 1 1 2 minus x, and then 3 minus x 1 times 1 block. So the determinant of our 3 times 3 matrix is the determinant of our 2 times 2 matrix times the determinant of our 1 times 1 matrix. So the determinant of the 2 times 2 matrix is 2 minus x squared minus 1 squared, and then times 3 minus x. So this is a difference between two squares. So it's 2 minus x minus 1 times 2 minus x plus 1 times 3 minus x, and this is equal to 3 minus x squared times 1 minus x. So we have two eigenvalues. Lambda 1 is equal to 1 with algebraic multiplicity 1, and lambda 2, which is equal to 3 with algebraic multiplicity 2. So now let us determine the eigenvectors for the eigenvalue 1. So these are the solutions to the homogeneous system of linear equations with the matrix of f minus the identity matrix. So it's a matrix 1 1 2 1 1 2 0 0 2. The first two rows are equal, so we can delete one of them. And the third row is 0 0 2, we can divide it by 2, so we will get 1 1 2 0 0 1. And now we use this 1 to kill this 2, so we get the matrix 1 1 0 0 0 1. So this is the row echelon form. So we can choose x2 as a free variable because the leading elements are in columns 1 and 3. So from the first equation we have x1 is equal to minus x2. For the free variable we have the trivial equation x2 is equal to x2. And from the second equation we have x3 is equal to 0. So in the vector form, x1, x2, x3 is equal to x2 times minus 1, 1, 0. So the vector v1, which is equal to minus 1, 1, 0, forms a basis in the subspace of all eigenvectors for f with eigenvalue 1. The second eigenvalue is 3, so let us determine all eigenvectors for the eigenvalue 3. So these are the solutions to the homogeneous system of linear equations whose matrix is the matrix of f minus 3 times the identity matrix. So this is the matrix minus 1, 1, 2, 1 minus 1, 2, 0, 0, 0. So here we can swap row 1 and row 2, and at the place of row 2, we add them. So we get 0, 0, 4. So we get 1 minus 1, 2, and 0, 0, 4. Now we divide row 2 here by 4 and use this 1 which we get here to kill 2 above it. So we get the matrix 1 minus 1, 0, 0, 0, 1. This is a row echelon form with leading elements in columns 1 and 3. So we choose x2 as a free variable. From the first row we have the equation x1 is equal to x2. For the free variable x2 we have the equation x2 is equal to x2. And from the second row, we have x3 is equal to 0. So in the vector form, x1, x2, x3 is equal to x2 times 1, 1, 0. And so the vector v2, which is 1, 1, 0, forms a basis in the subspace of all eigenvectors of f with eigenvalue 3. And this completes the example. So now we can formulate the main theorem about diagonalizable matrices. Theorem: a linear operator f from V to V is diagonalizable if and only if the sum of the algebraic multiplicities of all eigenvalues of f is equal to the dimension of V, and for any eigenvalue lambda, the algebraic multiplicity of this eigenvalue is equal to the geometric multiplicity of this eigenvalue. Let us start by proving the necessity of these conditions. Let n be the dimension of V. If, for some basis bold V in V, the matrix of f in this basis is diagonal, with lambda 1 and so on lambda n on the diagonal, then the characteristic polynomial of f is equal, so this is a determinant of the diagonal matrix with lambda 1 minus x and so on lambda n minus x on the diagonal. So this is a product of the linear terms lambda I minus x, where I ranges between 1 and n. So in particular, the sum of the algebraic multiplicities of all eigenvalues is equal to the dimension of V, because the characteristic polynomial is a product of linear terms. And also the sum of the geometric multiplicities is equal to the dimension of V, because we have an eigenbasis. And since we know that geometric multiplicities are at most the algebraic multiplicities, but their sums are the same, it follows that geometric multiplicity should coincide with the algebraic multiplicity for every eigenvalue lambda. So this proves the necessity of these conditions. Now let us prove sufficiency. Assume that the sum of the algebraic multiplicities of all eigenvalues is equal to the dimension of V, and that the algebraic multiplicity of every eigenvalue is equal to the geometric multiplicity of every eigenvalue. So let lambda 1 and so on lambda k be all different eigenvalues. For each I between 1 and k, let Vi upper j be a choice of linearly independent eigenvectors. So here j ranges from 1 to the algebraic multiplicity of lambda I. So we know that the algebraic multiplicity is equal to the geometric multiplicity, so this is well defined. What we want to prove that the collection of these vectors is a basis of V. And then we will be done, because the matrix of F in this basis, which by definition is an eigenbasis, is diagonal. So what we know that this basis contains exactly as many vectors as we need, because the sum of algebraic multiplicities is equal to the dimension of V. So it remains to show that the set bold V is linearly independent. So let us try to find out for which linear combinations of the elements in this set the linear combination can be the zero vector. So we consider a linear combination, the sum over all I and j, then the coefficient alpha ij times Vi upper j, and we equate this linear combination to 0. So here alpha ij are some undetermined real numbers. Let us apply to this linear combination the following powers of the linear operator f. So we apply f to the power m, where m is 0, 1, 2, and so on up to k minus 1. So k is the number of different eigenvalues. So applying f to the power m gives us the sum over all I and j, alpha ij, and then lambda I to the power m times Vi upper j. And this is supposed to be equal to 0 for any m. So this gives us k different linear equations. Recall that we have the following van der Monde determinant, so that the determinant of the following square matrix is non-zero. So if you consider the matrix where the first row is just 1, 1, 1, 1, 1, the second row is lambda 1, lambda 2, lambda 3, and so on, lambda k. Then the third row is lambda 1 squared, lambda 2 squared, lambda 3 squared, and so on, lambda k squared, and so on. So if you consider such a k times k matrix, and note that we have assumed that all lambda i's are different, then the determinant of this matrix is called the van der Monde determinant, and it is known that it is a non-zero number. So in particular, this matrix is invertible, and if we multiply with the inverse of this matrix on the left, so if we start from our system of linear equations, which we get here, so we have k equations, and we multiply the matrix of the system with the inverse of this k times k matrix on the left, we will reduce our system to the following system of linear equations, where we have the equation the sum over j, alpha ij Vi upper j is equal to 0 for I between 1 and k. And then here we can use that all Vi upper j, where I is fixed now, so these are linearly independent eigenvectors, and if we have such a linear equation, or alpha ij's should be 0. And this proves that our set bold V is a linearly independent set and hence a basis in V. And which shows that our linear operator, it has an eigenbasis and hence is diagonalizable. So here is an example. So we have seen the linear operator f from R3 to R3, whose matrix in the standard basis is 2, 1, 2, 1, 2, 2, 0, 0, 3. We have previously computed that this matrix has two eigenvalues, lambda 1 equal to 1 with algebraic multiplicity 1, and lambda 2 equal to 3 with algebraic multiplicity 2. We also computed that the geometric multiplicity of 3 is equal to 1. There was only one linearly independent eigenvector for this linear operator with eigenvalue 3. And 1 is smaller than 2, which is the algebraic multiplicity of 3. So the geometric multiplicity is strictly smaller than the algebraic multiplicity for the eigenvalue 3, and therefore this linear operator is not diagonalizable. Remark, there is one case in which the algebraic multiplicity for an eigenvalue is equal to the geometric multiplicity. And this is a case when the algebraic multiplicity is equal to 1. Indeed, if the algebraic multiplicity is equal to 1, then since it is equal to 1, so lambda is a root of the characteristic polynomial, the matrix of f minus lambda identity in any basis V is degenerate, so its determinant is 0. But then the corresponding homogeneous system of linear equation has at least one non-zero solution. In particular, the geometric multiplicity should be greater than or equal to 1. But since the geometric multiplicity is less than or equal to the algebraic multiplicity, then the geometric multiplicity is 1. So the problematic eigenvalues for diagonalization are eigenvalues for which algebraic multiplicity is strictly greater than 1. So in particular, we have the following corollary. If f has the dimension of V different eigenvalues, then f is diagonalizable. Indeed, if we have the dimension of V different eigenvalues, then all eigenvalues have algebraic multiplicity 1, and their number is the dimension of V, and then the geometric multiplicity for each eigenvalue is also equal to 1 from the previous remark. So we have this corollary. So here's an example how we can use this problem. Determine whether the linear operator f from R2 to R2, whose matrix in the standard basis is 2, 1, 1, 2, is diagonalizable or not. Solution. Let us start by computing the characteristic polynomial. So the characteristic polynomial is equal to the determinant of the matrix 2 minus x, 1, 1, 2 minus x. So this is 2 minus x squared minus 1 squared. This is a difference of two squares, so it's 2 minus x minus 1 times 2 minus x plus 1, which is 1 minus x times 3 minus x. So the characteristic polynomial is a product of different linear terms, which means that it has exactly dim R2, that is, two different roots. So because of the corollary, this linear operator is diagonalizable. Let us finish with some problems and questions. Question 1. Spell out with all details the argument in the lecture which used the van der Monde determinant. Question 2. Give an example of a linear operator on a real vector space which does not have any eigenvalues. Question 3. Determine all eigenvalues and eigenvectors for the linear operator on the set of all polynomials with real coefficients of degree at most 3, given by taking the derivative of the polynomial. Question 4. The linear operator g on Rx3 is defined as follows. G applied to f of x is the derivative of x plus 1 times f of x. Is g diagonalizable? Question 5. Let f be an invertible linear operator on V. Show that f is diagonalizable if and only if f inverse is diagonalizable. Thank you very much and see you next time.